wabarakatuh.
Waalaikumsalam.
Yeah. How about you?
Fine, ma'am.
Alhamdulillah. Yeah. You have a project which is due this morning. Yeah. And yeah, I think all of the group should have submitted by now. Now we will start with presentation. Yeah. So today we will use the time for presentation of the project. So that I will let you volunteering for that. Yeah. So who wants to present the result, and that will add as an activity marking as well. Okay.
Yes, ma'am.
Yes.
Maybe my group will present it now.
Okay. So who is the member of your group?
My member is Sultan and Anggito, William, and Timothy, ma'am.
William and Timothy. Okay. Anggito, you here?
Yes, ma'am. I'm here.
Okay. William.
Yes, ma'am. I'm here.
Okay. And Timothy.
Yes, ma'am.
All right. Okay. So I'll stop this first. Okay, you can try share the screen.
Okay, ma'am. Thank you, ma'am.
Have you seen my screen?
Yeah, we can see that already. You can slideshow the PowerPoint.
Good morning. Today, our team will present it about a numerical analysis project. There are Sultan, Timothy, Anggito, and William. Okay. First.
I want to explain about the problem of this that we get from the book of fundamental of heat and mass transfer. So the problem is conduction within the relatively complex geometry. It can be completed by using, it can be solved by finite difference method of this problem. So it has the two subdomains in this case. First is the rectangular one, and the second is the cylindrical one. It has the different control surface which is the case one. We have the two insulated with the inner of the cylindrical and inner of the rectangular, and then the outside of the rectangular. But in the case two, we add the insulated at T22 until T24. So this we have to find the temperature on each nodal, so we can solve it with PDE or and Gauss elimination. The next. So the known data is the case one. We have assumption that T1, T2, and T3 at the bottom of the rectangular is 20 degrees Celsius, and the T and delta X, delta Y, and delta R, it's the dimension of the nodal, each nodal. So we divide the subdomain into delta X and delta Y, which is 10 millimeter. And we add the heat generation 1000 watt per meter cubic, and the coefficient of conductivity is 10 watt per meter Kelvin. And next. So we divide the system into subdomains, which is rectangular and cylindrical. The rectangular one, we have nodal T1, T2, and T3 until T10 until T12. And the cylindrical, we at T10, T12 until T22 and T24. So we have the same nodal, which is T10 until T12, which is we have to solve it with in Q from the rectangular one and the Q from cylindrical one. Next. So we solve it with Laplace to find the basic equation, Laplace equation to solve the rectangular one and the cylindrical one. The left side is the cylindrical one, which is 2 quadrat t per dx square plus t quadrat t per dy square plus Q generation divided by conductivity. And the right side is the cylindrical. So, and if we put the A, B, C, and D into the ABC formula, we have D less than 0. So we get the Laplace equation is elliptic because D is less than 0. Next. So this is the finite difference form of the heat equation to solve the problem in rectangular one. So we have the it's the forward and backward PDE to solve Tm plus 1 plus Tm minus 1. So this is the central, and then the second one is the dt per dy. It's same with dt per dx. Okay.
Okay. And the next is the Newman boundary condition that we use to find the nodal where it's located in the exterior. So first step to do the Newman boundary condition is write down the basic equation from Laplace method, and then we take del t del x equal to t1g minus t minus 1g per 2 delta x. And because our case that most of external nodes is insulated, so the value of del t del x is equal to 0. So the final equation is 2t1g minus 2 delta x del t del x plus t0 g plus 1 plus t0 g minus 1 minus t minus 4 t0 g equal to 0. But after we write down this equation, we set the del t del x equal to 0 because it insulated. Next. And this is the example calculation for the rectangular. We took for the fourth nodal. The fourth nodal is located in exterior. So we using the Newman boundary condition like this. We set the equation and we cross the del t del x equal to 0 because it insulated. And then the final equation for nodal 4 is minus 4 T4 plus 2 T5 plus T7 is equal to minus 0.01. Next. And then this is for interior. The example for calculation in interior node, we take the 5 nodal. So the equation is still the same like the general equation, del quadrat t del x quadrat plus del quadrat t del y quadrat plus heat generation divided by coefficient heat transfer of conduction. And then we use the Laplace method with central scheme, like Anggito explained. And then, so the equation become T4 minus 4 T5 plus T6 plus T8 equal to minus 20.10. 0.01, sorry. Next. And then this is a calculation for cylindrical, the example for cylindrical. The equation is right down of the below of the figure. We took the exterior cylinder at node 40. No, this is interior. This is a calculation for interior node, and we took the Lapis method, the central shim Lapis method. So become T14 plus T15 plus I minus 2T15 plus 1 per R quadrat times T18 plus T12 min 2T15 per delta P quadrat plus Q dot per K equal to 0. Sorry, this is for exterior, not interior, because we solve for node 15 in cylindrical. So when we talk about exterior node, so del T per dr, del R is equal to 0 because it insulated in our case. So the equation is become this delta R quadrat T12 plus R quadrat delta P quadrat T14 minus 2 delta R 2 R quadrat delta R quadrat delta V quadrat times T15 plus delta R quadrat T18 plus R quadrat delta V quadrat T15 minus I equal to minus 1.38 times 10 power of minus 6. So, and then we took for the Newman boundary condition because it is in exterior. Next. Nah, and we took the del T per del R sama dengan del T del R equal to 0. And then we solved this and we found the equation for 15 nodes. This the equation is 0.00001 T12 plus 0.00028 T14 minus 0.0000478 T15 plus 0.0001 T18 equal to minus 1.38 times 10 power of minus 6. Next. And then this is a linear algebra equation in matrix form in forecast 1. And the next will presented by Mas William.
Okay, so this is it can be seen here that this is the matrix from the linear equation for case 2, which is containing 16 times 16 matrix. Next. Okay, so this is the in to solve the linear equation into the temperature value, we're using the Gauss-Jordan method. Is because that we are using the Gauss-Jordan method because the matrix of the linear algebra equation cannot form the diagonally dominant matrix. So meanwhile, when we try it with the Gauss-Seidel method, the difference between known temperature and the unknown temperature is large. So when the iteration running, the value will be detected as the infinite or too small. Then the value cannot be displayed by the MATLAB using the Gauss-Seidel. So we try to find another method using Gauss-Jordan, where which the value can be the value of the temperature can be found using the matrix identity. So the value of the matrix will be set to 1. So, and this is the matrix, identity matrix for case 1. Next. This is for case 2, where we can know the temperature value on the right side. Next. Okay, so this is the code that we input on the MATLAB. First of all, we have to define that size of our matrix using that M and N. The M is the number of row, while the N is the number of column. Then for the first part of the code, we have to make our matrix that we input to be pivoted. So it will make sure that the element on the diagonal dominant side will not be 0. And that's why this the coding. If ajj equals to 0, it means that checking the diagonal dominant is equal to 0. I mean the diagonally element. After that, it will be substitute the zeros diagonal dominant row with its below row. So if the condition is equal to 0, it will be changed into our substitute into the below row of the zeros row. And this system will be looping until the row of the diagonal element will not containing 0 value. That's why here is k equals to a 1 comma double dot. It means that the first row will be changed into will be substituted with the other row below the first row, and that will continue the iteration. After that, the second part of it is to make the upper matrix become 0. That's why here the code is ei equals to j plus 1 until n. It means that uh, column from j plus 1 until m, which is the number of row, will be calculated one by one until the upper side of the matrix will be 0, become 0. And then the third part of the coding is makes the lower become 0. The difference between the upper and the lower, in the lower we using j, which mean the row. So it will calculate uh, the 14 or 6, the last row of the matrix until the second row of the matrix. So it will not calculate the diagonal element of the matrix. Okay, next. Okay, so this is the last part of the coding, which making diagonal dominant value into 1. So to make it to identity matrix, the value have to divide by its self value. So to make sure that in the diagonal element it will be 1, and the right side of the matrix, which is the result of the temperature, will be divided by its value 2, by the diagonal element value 2. And after that, after the dividing process, the coding will display the result of the temperature value using xj equals to aj comma n. It means that the value that will be displayed is only the right side. Okay, so that's all for the coding. So here it can be seen that the MATLAB can display oh no, this is the input. This is the input for the calculation on MATLAB for the first case. Okay, so next will be explained by Timothy.
Okay, this is the result from the matrix. We found the case one. The highest temperature is 176.24265, and the lower is 0, is known temperature. This is for case one. This is for case two. The highest temperature is almost similar, but it is 179.05, and the lower temperature is 0 degrees Celsius. This is the temperature plot. This is for case one. The graphic is node versus temperature. This is for the case two, the node versus temperature two. This is the highest temperature. This is for the case two and case three. The graph will look similar, but there is a little different in node 15 and node 23 until 25. This is a conclusion. Temperature between case 1 and case 2 are little bit different. When node 22, node 23, and node 24 are insulated, temperature for each nodal become 0.3, 0.046, and 51.81 degrees Celsius. Node 23 and 24 are increased from 0 degrees. The maximum temperature increase on node 11 from 176.243 degrees Celsius to 179.0.5 degrees Celsius. It can be concluded that insulating node 22, 23, 24 will increase the temperature along the workpiece. Okay, that's all from our team. Thank you. Hello, ma'am.
Ibunya nggak ada. Ibunya masih ini disconnect.
Recording in progress.
Yeah. Sorry, it looks like I've been disconnected. Can you repeat a bit?
A conclusion.
Last one is about the plot for temperature. Yeah, that one. Okay. So is this the last slide?
The temperature
Okay.
is start from here.
Okay. Yeah. The last one after this. Okay. So only the conclusion, yeah.
Okay.
Okay.
The conclusion.
Yes.
The first conclusion is temperature between case 1 and case 2 are
Recording
little bit
stopped.
different. When node 22 and node 23 and node 24 are isolated, the temperature for each nodal become 0.30546 and 5.181 degrees Celsius. Node 22 and 24 are increased from 0 degrees. The maximum temperature increased from on node 11 for 176.243 degrees Celsius to 179.05 degrees Celsius. Can be concluded that insulating node 22, 23, and 24 will increase the temperature along the workpiece. That's all, ma'am. Thank you.
Yeah, thank you. Okay, so this is interesting because you have to defining on two axes, yes, which is rectangular and rectangular coordinate and cylindrical coordinates. Yeah. Okay. Now we will have a short discussion. Is there any question to this group? Yeah, is there any question to this group? Okay, so you have that discretization, yeah, discretization, which is rectangular on the bottom side and cylindrical on the upper side. And what coordinate that you use to define the nodes, which is in the interface between the rectangular and the cylindrical one?
May I answer it, ma'am?
Yes.
We use two of them, and we solving for with the first one we solving with the rectangular, and then we found the heat flux for the node 11.
Okay. Can you show it? Can you show the the nodes? Yeah.
Okay, this is ma'am. For example, we take the node 11
Yes.
in interior, the interface. So the first step, we using the rectangular one to found the Q flux for the T11 for rectangular. So the temperature distribution equation is, if we develop again, we will have the correlation with the heat flux, right, ma'am? And then, so we using the rectangular for finding the Q flux on node 11, and then we using the cylindrical coordinate at node 11 too for finding the Q flux too, ma'am. So from the theory, we know that Q flux in this rectangular and the cylindrical one in same node is exactly same, right, ma'am? So we can substitute the key flux from the rectangular to the key flux in cylindrical. So the heat flux will eliminate and the equation is fully function of temperature, ma'am.
Okay. Do you have the calculation for note 11?
Let me share screen the PDF.
Yes.
Okay. This is the calculation.
Yes.
11 not delta.
Oh yeah, wait.
All right.
So this is 10 note. Yes, this 11 note.
Yes. So this is note 11. So that you have T. Can you show in the regular
Okay, ma'am.
view?
Sorry,
Yeah,
sorry.
it's very small.
I'm sorry.
Yeah, okay. So 11, note 11. All right, here you have the heat flux. Yeah, so you're calculating the heat flux there. All right. Okay, so you are calculating based on the heat flux. Yeah, all right. Okay. Okay. Okay, so this is, I think this is correct already for the calculation. Yeah. And you use the heat generation as the source term. Yeah. So in this case, you have heat generation for the source term. Yeah. I think it's very good. Yeah, that you can combine these two coordinate for the analysis. And one more is about the sulfur. Yeah, the sulfur. So you are using Ghost Jordan. What was the problem if you are using Ghost Seidel or other method? I think you have mentioned that earlier.
Yes, sir. So when we try using the Gauss Seidel, and we input for the code on the MATLAB, it displayed that the after the second iteration, the value is too small, man. It's like 0.00000
Mhm.
like that, and then it defined as the infinite, and the value will become none or undetected. So we try to solve it with the Gauss Jordan, which can make it easier with make the diagonal the matrix into the identity matrix. So after that, the value can be found rationally.
Okay. Yeah. So this is just a little suggestion. Yeah. So if we look at here, we see that the order of the number is very different. Yeah. So what you have from the from the rectangular coordinate was as the order of 1 approximately. Yeah. But for the the discretization that you get from the cylindrical axis, you have up to power of -5 or 6. Yeah. So it's very large different. So this is a suggestion. If you have a very large difference on the order of the magnitude of the number, so what you can do is do scaling. Yeah. So you can do scaling to the equations. So for example, you divided, you multiplied the equations that you have from the from the cylindrical coordinates, yeah, with, for example, uh, uh, 10,000 or 100,000, yeah, so that you have an approximately the same order with the value, yeah, with the value of the coefficient that you get from the rectangular. So with that, yeah, I think the case when you use cosine is that because of the rounding error, yeah, the rounding error, because the value, as what we have learned before, yeah, if the value has different magnitude, very large difference in the order of the magnitude, so that will result in a very large round of error. So that in this case, you have tested that you have a diverged solution because of the round of error. So yeah, this is for a suggestion if you have a very different order of magnitude, yeah, so that you can do scaling. Yeah, you can do scaling. Yeah.
Excuse me, ma'am.
Yes.
I have tried to do scaling, ma'am. I times 1 million in every side, and in the MATLAB still do rounding, ma'am. So is 1 point, example 1.2 times 10 power of 6, ma'am. So in the sum part, the coefficient becomes 0.10.6, ma'am. 0. Yes, ma'am.
Does it mean that all of the value is already changed if you use the scaling? Can you repeat the problem?
Izin pakai bahasa Indonesia.
Yeah.
Jadi gini, kemarin saya sudah mencoba untuk di scaling pakai 1 juta, saya kalikan 1.000 dulu semuanya. Nah, ternyata yang 1.000 masih kekecilan, terus saya coba kalikan pakai 1 juta. Nah, waktu di hasilnya itu untuk angka-angka yang besar itu, jadi hasilnya itu misal 1 juta, jadi dia nulisnya 1 kali 10 pangkat 6. Jadi untuk yang angka-angka yang sudah saya, misal yang ini yang 0,00138 itu nanti jadinya 0,10 pangkat 6, jadi 138-nya itu hilang. Jadi MATLAB-nya tetap membulatkan, jadi dia cuma 10 pangkat 6 dikalikan 10 pangkat 6.
Sejak awal input sudah diubah ya? Sejak awal input.
Dari mengolah data di Excel, dari penyusunan matriks.
Enggak, kalau ini kan nilainya kan apa? Artinya kan 10 pangkat 0 nantinya, bukan begitu kalau dikalikan 10 pangkat 6.
Jadi dia itu kalau diperpanjang itu 0,0000138 kali 10 pangkat 6. Iya, dia ngikutin pangkat terbesar yang ada di bilangan itu, mem. Di antara matriks di antara bilangan-bilangan di sebelahnya.
Tapi kan maksud saya yang lain kan tidak di scaling ya. Artinya hanya beberapa equation ini ya yang nilainya besar.
Saya scaling semua, mem, dari awal.
Jadi yang 4 itu juga di scaling ya?
Yang 4.
Yang dari rectangular coordinate juga di scaling?
Iya, mem.
Oh ya. Ya, yang di scaling hanya persamaan yang kecil aja sebetulnya. Ya, kalau yang persamaan sudah ordernya 1 tidak perlu di scaling lagi. Nah, ini mungkin saran aja ke depannya ya. Jadi bisa jadi itu terjadi karena itu tadi ya, keterbatasan dari significant digit. Tapi ini berhasil ya dengan Gauss-Jordan ya.
Gauss-Jordan berhasil, mem.
Ya, mem, berhasil.
Oke, baik. Ya. So I think this is good. You have given an effort there, and if I look at how you calculate the heat flux there, it's very similar to what we do in finite element analysis. Yeah, so that you treat it like an element, and there is a heat flux that goes through the element. Yeah, okay. All right. So yeah, I think this is very good. Any questions from the others? Okay, and one more suggestion is that if you can plot the contour of the temperature, that will be very good as well. Yeah. All right. So thank you for this group. You can close the presentation.
you, ma'am, for the time.
All right. Okay, so very nice presentation from the first group. Yeah, which is we have seen that there is a complexity in combining the rectangular and cylindrical coordinates in the discretization. Yeah, and it's also using two types of boundary condition, which is the Dirichlet boundary condition and Newman boundary condition. All right. Now, who wants to go second?
Excuse me, ma'am.
Yes.
I think my group will present for the second attempt, for the
Okay.
second chance. Okay.
Right. Anggarda.
My group is Anggar Darian, Abi Surya,
Okay.
Fauzan Zaki Surya Putra, and Raffi Fadlur Rahman.
Okay. Now you can start the presentation.
Okay. Fauzan. Okay, now we will start the presentation. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning, everyone. Good morning, Ms. Vivian. And today we will present our project about numerical analysis and the PD elliptic problem. So our group consists of Raffi Fadlur Rahman, student number 10, Abi Surya Dewantara, student number 16, Angga Darian Ardana, student number 106, and Fauzan Zaki Surya Putra, student number 123. Next. So this is the problem, our problem. So we have Mr. Bennett here. He is an engineer of a logistic company. He is tasked to design a laser weight scale for the cement. And the company gave him two choices of plate for scale. Both plates are square with a thickness of 2 cm. The type A plate has an elastic modulus of 73.1 gigapascal, usually known with aluminum 2014, with weight of 1.5 millimeter. And type B plate has elastic modulus of 68.9 gigapascal, also known as aluminium 6062, with a weight of 1 meter. Both of them are. Oh yeah, I'm sorry, Miss. There will be some discrepancy between the presentation and the report. So I will point out the discrepancy. Thank you. Now we will continue. What this mean? What the both have the same width and thickness mean that both of them are square. Both of the aluminum are the square plate. And to maximize the sensitivity of the scale, he must choose which type of plate to have most deflection under loading. And we assume that the plate is simply supported. The load weight is distributed as an areal load of Q. The maximum load will be 1,000 kilogram. That will be the load that we will use. And the delta Y equals to delta X, which is equal to 0.25 centimeter. And Poisson ratio for both aluminum are the same, which is 0.3. And the main problem is which springboard should Bennett use. So in this case, Bennett will choose plate with high deflection as opposed to the low deflection plate. Next. Okay, for the equation, it will be explained by Abi.
All right, thanks. Thank you, Rian, for the time. In this problem, we use the deflection formula from the Stephen Chapra book in chapter 32.2. We have this fourth order PDE of Z, X, and Y equal to Q per D. Now, we can't solve the equation as it is, so we must assume U as D squared Z per dx squared plus D squared Z per dy squared. And then we found the first PDE, the first second order PDE as d squared u per dx squared plus d squared u per dy squared is equal to q per d. Q here is the aerial load applied with the dimension of Newton per meter squared per d. D is, we can see D in the next slide. Okay, so D is flexural rigidity. It is equal to E, the Young's modulus, times delta Z cubic. That's the thickness of the plate per 12 times 1 minus Poisson ratio squared. And then for the, since we are looking for the maximum deflection, we have the analytical method to find the maximum deflection. That is ym is equal to 0.124142 times p. P in this equation is equal to q from the previous equation times b. B is the width of the plate to the power of 4 per Young's modulus times t. T in this equation is equal to delta z to the power of 3 times 2.21 times b per a. That's the width and length of the plate. Since we are using a square plate, this is equal to 1 plus 1. And then next slide. Now, the discretization method we use here is for order PDE, which we expand as two second order PDE, and then we use the central divided schemes to solve the problem. Ui plus 1j minus uij minus 2 uij plus 2 minus plus ui minus 1j is per delta x squared plus uij plus 1 minus 2 uij plus uij minus 1 per delta y squared is equal to aerial load per flexural rigidity. And then this is the solver we use, MATLAB software, which will be explained by Raffi.
So before we get to the code, we'd like to share our result and the analysis. This is from MATLAB. So the type A with the data showed in the screen, we can get the matrix of the nodal that we plot in this table and at the left side of the screen. As we can see, the edges of the plate are, all of them are zeros. There is no deflection there because those nodes are supported, so they don't move. And the maximum deflection is at the middle node because it is the least supported node of them. So at the right side of the screen, here we have the counter plot of the deflection. So the maximum deflection is at the center of the board, as said earlier, at 0.0016 meter. And this is coming from the 15th iterations. And then this is for plate A, and for plate B here is this. And here the plot is smaller than the type A. The type A we use 7x7 plot, 7x7 node. And in B we use only 5x5 because the size of the plate in question is smaller, but we use the same delta. And same as the type A, the left side table is the matrix of the deflection, and the right side is the plot. Here the maximum deflection is at 0.00077485 meter, and coming from 7 iteration. That is from MATLAB, but from the analytic earlier that we use mathematically, the maximum deflection here is for type A, 1.6677 times 10 to the power of -3 in meter, and type B is 7.87305 times 10 to the power of -4 meter. So there is a slight difference, but the difference is small enough to make the iteration accurate enough. So the next slide is the conclusion. So the conclusion is Mr. Bennett in question. He should choose the type A plate because the type A plate deflects more than the type B, and more deflection means more difference in the laser detection for his laser weight. That makes the weight that he's about to design more accurate. And that's for Bennett, but for the analysis, we can see that the less tolerance in error that apply to the operation will result in more accurate estimation. And as the number of nodes increase, we have to decrease the tolerance to get more accurate estimation. In this presentation, we will show an example of the same simulation, but with more nodes in the end of the presentation. Here's the code.
Okay, I will explain about the code that we use. So the flow of the code that we use to solve the problem is, first we define the dimension of the plate. First, the n is the node that we use. For plate A, we use 7 node because for the dimension of the plate, we divide it by the different or the distance of the each node. That means the node that we use is 7. And after we define each dimension, we define the x and y, which is the line space means the point between the plate, that at x coordinate we use from 0 to w we use n point, and for y, we use 0 until L have the have endpoint. And then we define the matrix by zeros the n, which is we will have the 7 by 7 matrix. Okay, and then we set the boundary condition, which is we know that the problem has a simply supported beam. That it means that there is no deflection at its side. So we define at its side has the zero deflection shown by the code. And then for the solving the equation, first we set the goal that which is the toll that we set at 10 power of minus 20, and for the first error equals to 1, and for the first iteration from 0. Okay, for the iteration operation, we define that the operation will occur until error will be less than the toll. So when the error still greater than the toll, the iteration will be occur. So we put the error while the error greater than the toll, the iteration will occur, and we set the u out equals to u, which is it define the error letter. And then for the index I, for index I at the x coordinate, we will get the number of deflection at 2 until n minus 1, and for j at the y coordinate from 2 until n minus 0 and n minus 1. And for the equation that Abi explained earlier, we will get the result from this equation, and when so the operation will end for the j and for the I, and for the error we define as the maximum number of different when u alt minus 0. So when the maximum of each node, the error still greater than the toll, the iteration will occur. But because we take the variable of u to define the x square by the z square by per the x square plus the dz square dz square per dy square. So actually for the goal we're looking for the z, not the u. So we doing the iteration again for the u, so we can get the z. With the same method, we define the matrix of the z, which is n by n matrix, and we define the boundary condition, and we set the toll error nk to, and for the operation for the u, same as the for the u earlier, and for the equation we use that for the almost same equation, but the difference is at the uij. This is the what is it? The exact value at the node of the u, and when the iteration begins and the error has the value less than the toll, so we can get the matrix that shown by Hausen. And after we get the matrix, now we will plot the matrix by subplot at 1 1 1, which is the position at the window, and we use the code of surface minus z, which is we will get the surface plot of the z by the matrix that we get earlier. Okay, and we set the name of the coordinate and the color bar that will explain the number of deflection. Okay, this is for code type A, and actually not different enough from the type A. For the type B, we use the node is 5 and same amount of dx, and the same operation from the type A, but actually from the when we try to solve this problem, we try to set the toll when what will the result when we have the greater toll, and what will happen when we decrease the toll. So when Fauzan explained the conclusion, we know that when the toll is get less number, the result will be accurate from the analysis. So this is why the toll is very small that we use. And for the next slide, this is the example of when we use the huge number of nodes, but we need to less the tolerance, so we can get the number that have lesser error than the analysis. Maybe that's for our presentation about the project. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Assalamualaikum warahmatullahi wabarakatuh. Yeah. So in this case, we have different problem, which is relates to the deflection. Yeah. So this is relates to the structure. And here it's using the basic equation is fourth order. Yeah, fourth order PDE. So we have a fourth order PDE in which that can be reduced into two equations of second order PDE. So this is very interesting, yeah. So that you need to do the calculation twice, yeah. First is for the equations to find the PDE to find the value of u, and then the next is the calculation to find the value of z, which is the fraction itself. Yeah. So that in the solution method, so you are using Gauss-Seidel, yeah. So the value which is updated is correctly directly used, yeah, for the subsequent calculation. All right. Okay. Any questions to this group? Yeah. So if we compare the code for type A and type B, is this only the difference is only the tolerance and the number of nodes, isn't it?
Yes, ma'am. And the dimension.
The dimension, because the number of nodes is different, yeah. So you use delta x is the same, yeah.
Yes, ma'am.
Okay. All right. So basically, it's the same code, but you vary the number of the node, yeah, and also play with the tolerance level, yeah, in which that will stop the calculation. Okay. So this is good already. You have the surface, yeah, to display the contour, the surface plane, and yeah, about this one, yeah, this in this figure, yeah, we have the temperature, the deflection is not zero at one at two of the sides there. Yeah, is it because of the storage of the memory for the nodes, or yeah? If we look at it, we have 60 by what is 60 notes? Yeah, 60 notes is correct. Yeah, but yeah, so we see here that it's following the boundary condition that is applied on the sides. Yeah, but for very small notes, it looks like, yeah, it's not zero. Can you explain that?
Okay, ma'am. Fauzan, can you show the previous plotting? Okay, so ma'am, we kind of have the same question about it. We discussed it last night. So in our discussion, I think why this the face here is yellow, but the one across it is blue, is because the face is actually using what interpolate the value on this node and this node to this two nodes. So I think they use dominantly this node. So how do I say? Can I use Indonesian, ma'am?
Yeah.
Oke, jadi konklusi dari kami itu, ma'am, space ini dia mengambil nilai dari noda yang lebih awal gitu, ma'am. Jadi yang ini itu noda 0. Jadi untuk face-nya dia ngambil noda yang di sini, terus untuk face yang ini ngambil noda yang kedua, dan seterusnya. Nah, itu kenapa saat di yang nodanya banyak, can you Fauzan, can you go to the last? And then because this has more nodes, so they have more data to process, ma'am. So you can see that even though with this much more nodes, we can still see the difference in color, just very tiny difference, ma'am. So, but still, the face is will still use the color of the dominantly use the color on the previous node.
Okay, so is that, yeah. So what you mean is that the color is basically the color of the element there or the surface will follow the value of the node before that. Yeah. So
yes,
sort of a backward approach there. Yes, because we have a finite difference, not a finite element. Yeah, so that will be calculated based on the value before. Yeah. Okay. All right. Yeah. Okay. So I think that is acceptable. Right. Any other question from the others here? Okay. So if there is no questions, you can close the presentation.
Okay, we will close the presentation. Thank you, ma'am, for listening to our presentation, and thank you, everyone, for joining this presentation. I'm sorry if there's any mistake in our words. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
And ma'am, I want to ask something.
Mm-hmm.
So there is some discrepancy on our presentation and on our report. So on our report, we type second order, not for order. So should we re-upload the report, or
is it the result is the same as this one?
Yeah, the result is the same. It's only typo here and there.
Oh, okay, so that's fine. Yeah, so that's fine. You don't have to upload it again. Yeah, we have seen the presentation. I think that will be enough. Yeah, so that's fine. Yeah.
Okay, thank you so much, ma'am.
Yeah. All right. All right. Thank you for the second group. Now we have seen two very interesting presentations today. Now we go on to the third presentation. Who wants to go next? Yeah, the third presentation today. Who wants to go next? Okay, if there is no one wants to go next, I will call a name. Yeah. Yes, Farhan.
Maybe my group will present.
Okay. Okay, so Farhan will be presenting next. Who is the member of your group?
My member is me, and then Salwani Serina, Agnes, and Harvin.
Okay. Okay. So everybody is already here. Salwa, you here? Okay, Salwa is.
Yes.
Yeah, okay. Agnes, you here as well?
Yes, ma'am.
And Harfin.
Yes, I'm here.
Okay. All right. So yeah, you can slideshow this one. Yeah, you can start the presentation.
Okay. Excuse me. My let me. Okay, let me try to present our group project. Maybe Salwa can click next.
Okay, this is our problem. There are a small 3 centimeter times 3 centimeter sample of thin plate with temperature boundary and some variation. In here, we use 2 variation. The first is boundary condition, and the second is number of nodes. Okay, this is the variation 1 and boundary condition 1. We use temperature use 115 degrees Celsius and 75 degrees Celsius, and the last is 100 degrees Celsius. The second boundary condition is we use 100 degrees Celsius, 25 degrees Celsius, 150 degrees Celsius, and the last is 90 degrees Celsius. The next variation will be explanation by Agnes.
Okay, so for the second variations, we use different number of nodes. The first nodes, we use 10 times 10 grids, and then with the same temperatures. For the top one is 25 Celsius, for the right one is 150 Celsius. For the bottom one is 90 degrees Celsius, and the left one is 200 Celsius. Next. So for the second type of number of nodes, we use 5 times 5 number of nodes with the same temperatures. Next. Okay, so for the basic equations, we use the equations based on the Laplace equations. Here we have to find through the iterations, we have pi plus 1 for g, and then plus pi minus 1 for g, and then pi g plus 1 plus pi g minus 1 divided by 4. Next. Okay, so we use the second order linear partial differential equations, where we have two independent variables and then the position to x and y, and the centrals some equations. Next.
I will continue the presentation. So we have the first temperature distribution for the first variation. So we have the first variation is the temperature boundary layer or boundary condition variation. So we can see here that we have in the left side 50 degrees Celsius in the temperature, and the right side 75 degrees Celsius, and both bottom and upper side we have 100 and 150 degrees Celsius. So we can see that the temperature is increased from bottom to the upper side, and then instead it is decreased from the right side to the left side. And we can see that the lowest temperature is in the plate, in the middle of plate, is 29.413 and 8 degrees Celsius. Okay, next. Then we have the other variation. So we vary the temperature as the boundary layer. So you can see that we have a different temperature as the boundary layer at the left, right, upper and bottom side. So in the right side, we have 150 degrees Celsius. In the left side, we have 200 degrees Celsius, and bottom and upper side, we have 90 degrees Celsius and 25 degrees Celsius. So in this variation, we can see that the temperature increase from the upper to the bottom side, instead is decreased from the left to the right side. And same with the variation before, we can see that the lowest temperature is in the middle of the plate, is 39.2990 degrees Celsius. And it is the different variations. So in the first variation, we varied the temperature boundary layer, but in the second variation, we varied the amount of the nodes. So basically, we use 10 times 10 nodes, and it is with the same temperature as the variation to in the previous temperature distribution. So yeah, in this slide, you can see that it's 10 times 10 nodes. Next. So how about if we change the nodes becoming 5 times 5 with the same temperature boundary layer? So actually the increasement and the decreasement, it's quite rough. It's rougher than the previous slide. So yeah, but basically it's same that from bottom to the upper side, the temperature is decreased, and from left to the right side, the temperature also decrease.
So this is the method that we use for solving the equation. We use the Lippmann method, or also known as Gauss-Seidel method. And input the value to MATLAB in a series of codes. Next. This is our result, the surface plot graphic from the variation 1 and boundary condition A. It is next. Okay. Then this is the second the variation 1 of banded, but with the second boundary condition B. And this is also the variation 2 with number of nodes A. And this is the last variation with the less number of nodes, which is number of nodes B, and variation number 2.
So for the conclusion, we can conclude that temperature difference will affect the neighboring nodes to change the temperatures because there are a different temperature, so the heat transfer will occur there. And then heat transfer will occur from higher temperature to the lower temperature. Therefore, temperature will distribute from higher to the lower regions. For variation 1, boundary condition A, from top to bottom, the temperature decreases and increases again in the middle of the plate, and the lowest temperature is in the middle of the plate. It occurs because the right and left temperature boundaries are lower than the bottom boundaries. And for the variation 2, boundary condition B, as we can see before, that from top to bottom the temperature increases, then decreases. From the bottom to the top, the temperature decreases, then increases again in the middle of the plate. Yeah, it's same with the variation 1 boundary condition A, that the lowest temperature is on the middle of the plate. It occurs also because of the right and left temperature boundaries are lower than the bottom. I'm sorry, there's a little bit typo here in the presentation for variation 2 boundary condition B. And for the variation 2, that we vary the number of nodes. The number of nodes B, it is 5 times 5 nodes. The number of nodes is half of the other variation. This causes the plot to be less accurate because less point of interest is analyzed. Therefore, the plot surface is less smooth. So basically, the increasement and decreasement is not as smooth as if we use 10 times 10 nodes. Okay, next.
Okay, this is the code that we use in MATLAB. The first section is we clear the workspace. This is done so that when we rerun the code over and over, the workspace is not overloaded. And the second section is we input the data that depends on the variation of the nodes, and X and NY 10 times 10 or 5 by 5. And LX or LY is the length of the plate that we analyzed. Next. The next section, we input our grid so that we can analyze in the plot X line space of from 0, LX and NX. That means the number of plot is NX with increment of LX from 0. And dx or and dy is the difference between the nodes. The next section is we create initial guess for the actual solution. We start from 0 from all of the value zeros, t equals zeros of nx and ny. The next section, we input our boundary condition initial value from variation 1 and variation B depends on the value input. Next. The next section, we input our boundary condition from all of the exterior of the matrix. From the top left, right, top left is bottom boundary for j equals 1. We input j equals 1. It is from the bottom of the matrix, j equals 1. For I equals 1 until I equals nx, Tij equals to T bottom, the bottom of temperature. The top boundary, J equals Ny, which is 10. For I equals 1 to I equals nx, Tij equals T top. And we repeat for the left and right boundary depends on the value of temperature. Next. Then we apply the Lippmann method or Gauss-Seidel method to loop the function for all of the interior grid points. We don't do the loop at the exterior because the boundary is already fixed from the previous section. We use 7 iteration so that the error is very small. For iteration 1 until 7, we loop for I equals 2 until I equals nx minus 1 because the I equals 1 is included here because we only use the interior of the matrix and not until nx, rather nx minus 1 because for the same reason only we calculate the interior matrix. We then also calculate for the column side of the matrix j equals 2 until j equals ny minus 1. With the same reason, we don't calculate and loop the exterior, only 2 until ny minus 1. And the equation is Tij equals Ti plus 1j plus Ti minus 1j plus Ti plus Ti j plus 1 plus Tij minus 1, all of that over 4 divided by 4, and we end the code. Next, we then plot. Next, we then plot the solution with a surface plot with this code and label x, y, and z coordinate and name the title. The last thing we do is we transpose T to get temperature distribution that corresponds to configuration. Next. Okay, I think that's it from our group presentation. Thank you for your attention. I will give it back to Ma'am Vivian. Thank you.
Yeah, thank you. So we have a case here in which we have a plate and want to find the temperature distribution of the plate. Yeah, so in this case, you have 4 variation, is it? Yeah, 3 or 4. You vary the number of nodes and vary the the boundary condition. Yeah, in which for the boundary condition, all is using Dirichlet boundary condition. Yeah, or the temperature is fixed. Yeah. All right. And here you are using Gauss-Seidel for the iteration, yeah, for the solution method. Yeah, in which the code can be used generally for all of the variation. Yeah, so you can just change the temperature, for example, of the boundary, and also change the number of the nodes. Okay, so I think that is pretty good. Do you have the yeah, so can you show again the result of the temperature distribution? Yeah, so you have that temperature distribution and it looks like similar, yeah? So a total of 4 variation, yeah? 2 boundary condition, and the second variation also it's only 3, yeah? Number of nodes, nodes A and B, so a total of 4. And what is the number of nodes that is used for the boundary condition? Here.
Sorry, I'm sorry, ma'am. Pardon, what do you ask? I don't hear it clearly.
Yeah. What is the number of nodes that is used in the variation of the boundary condition? Is it 10 by 10? Yeah.
Yes, ma'am. It's 10.
Okay, so 10 by 10 using 2 boundary condition, and then the next variation for the number of nodes. So that is tested for both boundary condition as well. Yeah. Is it?
For the second boundary condition. So basically we have 3 different variations.
Yeah, so it's only three variation, yeah. So
Yes.
that yeah, okay. So 3 variation, but you show four graphs here, yeah. Okay. All right. So 3 variation in total. Okay. Any question from the other? Yes, Sultan, you want to ask? No?
No, ma'am, it's pretty clear.
Okay. All right. Okay. So thank you for the third group. You can close the presentation. Okay, so the last presentation today, we did the 4th presentation. And is there any of you who simulate using irregular boundary? Is there any of you who simulates using irregular boundary? No one? All right. So if you can simulate using irregular boundary, that will be good as well. Yeah, we have discussed about that. All right. So who wants to go next for the fourth presentation today? The last presentation. Who wants to go next? Okay, Fifi, you here? Fifi Bella?
Yes, ma'am, I'm here.
Yeah. Can you present your result?
Yes, ma'am. Please wait a minute, ma'am.
Yeah. Who is your group member? Okay, you can start the presentation. Is everybody here? Benedicto Bona, you here?
Yes, ma'am.
Okay, Derivata Nico
Yes, ma'am.
and Yosef. Okay, you're presenting.
Yes, ma'am.
All right. Yeah, you can start the presentation.
Good morning, ma'am, Vivin, and everybody. Today, we are going to present our project about the two-dimensional cube of non-circular cross-section. Maybe anybody we can start from Nico, maybe.
The first is the problem. we choose this geometry. Next slide, Chef. This is our boundary condition. The first is the outer surface is adiabatic, and the second is inner surface has boundary dou T per dou R equal to dou T per dou Y equal to 20. And the third is bottom surface has boundary dou T per dou Y equal to 100. This is our initial position of nodes. We have 17 nodes, and the angle is 30 degree, and delta x equal delta y equal delta r is 10 millimeters. Our group choose two variation. The first is delta angle from 30 become to 50 degree, and the second variation is the bottom surface from dou T per dou Y equal to 100 become to 0 or adiabatic. The picture from variation 1 is left one, and the second is the right one. This is the basic equation and the elliptic from AB from ABC. For heat conduction in two dimension at steady state condition have the first is Cartesian coordinate and the second is polar coordinate.
Okay, the next is discretization method. In here we use first and second order central divided difference with second order error with two types of coordinates, first Cartesian coordinates and polar coordinates. For Cartesian coordinates, dou T over dou X equal to Ti plus 1j minus Ti minus 1j over 2 delta X. Dou T over dou Y equal to Tij plus 1 minus Tij minus 1 over 2 delta Y. And for polar coordinates, dou T over dou R equal to Tr plus 1 theta minus Tr minus 1 theta over 2 delta R, and dou T over dou theta equal to Tr theta plus 1 minus Tr theta minus 1 over 2 delta theta.
So next I will explain about the linear algebra equation. So this time we will look at the first condition first, the initial condition, which have 17 nodes. Next. So for example, I want to calculate the T1. So in this case, we take the equation at I'm sorry, I mean the calculate at T2. So we take the calculation case 1a and case 1b, which we made ourselves. So from the polar and Cartesian equation, we can derive it and we get the equation as in the slide. And because the right side is insulated, so it can be assumed that delta T per delta R equals to 0 and delta T per delta theta equals to 0. So the final equation is the last one. Next. So for the note 1, we use case 1b that we derived before, and we input the number and we get the linear equation. The same procedure is repeated for all of the nodes with different cases. So when we already get all the linear equation, we put it in matrix. To make it easier, we do it in Excel by writing the matrix one by one based on node and based on the temperature. Next, we do the same thing for the second condition, which has 26 nodes with delta theta is 15 degree. Next. We get the matrix. Next. After that, for the last one, we have the same delta theta 30 degree and 70 nodes, but with the outer one is adiabatic. So it's supposed to be delta T per delta Y in the bottom surface is 0. And we get the linear equation too. Next.
Okay, this is the solver being used to solve the linear algebra equation. In this project, the calculation process is carried out using the Gauss-Jordan method in the MATLAB application. The calculation process is start by entering the matrix coefficient input in the MATLAB command window. After that, the coefficient matrix entered. The next process is to enter the vector matrix. After the vector matrix is entered, the program code will perform the augmented matrix formation. And after that, the program will perform a looping process to make each pivot entry and all the entries 0 below and above each pivot entry. After the condition is reached, the program will stop and display the result in the command window.
So based on the calculation we do on MATLAB, we get the temperature on each nodes as presented on the slide. The first picture is the number of the nodes, and the middle picture is the temperature on each nodes, and the last one is the graph temperature on each nodes. So based on the calculation, the temperature on node 3 is lower than temperature on node 2, and the temperature on node 2 is also lower than temperature on node 1. So this phenomenon it also happen on node 4, 5, and 6. So the outer diameter has higher temperature and the inner one has lower temperature. This can we assume that this can be caused because the lower temperature field located inside the tube. And also on node 7, the temperature is lower than temperature on node 8, and the temperature on node 8 is higher than temperature on node 9. So there is an anomaly in there, and but only slightly. And then this is also happen on node 10, 11, and 12. After that, the temperature on node 13 is the smallest one for the node within inner diameter. So between T3, T6, T9, and T12, and T13, the smallest one is in T13. We assume that this can be the temperature is smallest at node 13 because the large area exposed to the field inside the tube. Also, on the bottom surface, the largest temperature is on node 14, followed by node 16, 17, and 15.
Okay, now I will explain the comparison between the initial condition and second variation. On the second variation, the bottom surface is insulated. The temperature on node 3 is lower than temperature on node 2. The temperature on node 2 is lower than the temperature on node 1. The phenomenon also happen on node 4 and 5 and 6. As the node closer to inner diameter, the temperature is decreased. On node 7, the temperature is lower than the temperature on node 8. The temperature on node 8 is higher than the temperature on node 9. This phenomenon happens because the heat is coming to cylindrical subdomain from rectangular subdomain, mainly from the middle diameter between inside and outer diameter. On node 10, the temperature is higher than temperature on node 11. The temperature on node 11 is lower than the node 12. The temperature on node 13 is the highest one for node with inner diameter. This can be caused by the insulation at the bottom surface that cause the temperature around it to rise. On the bottom surface, the largest temperature is on node 17, followed by node 14, 16, and 15. On the graph above, the variation of the temperature line is similar with initial condition temperature line up until node 12. For node 13 until 17, the temperature line for initial condition is lower than temperature line for second variation. This is because the bottom surface of tube is insulated.
Okay, so for the conclusion is for the initial condition, the temperature of each node depends on the coordinate or position of the node. So more closer the nodes to the inner diameter, the temperature will be decreased. And for the first variation, it was found that the data is incorrect, and incorrect calculation resulted in the result that were not expected. So the calculation results are not accurate. And for the second variation, it is quite similar as the initial condition, but there are some difference from node 13 to node 17 that from the graph before shows that the trend line for the second variation is higher than the initial condition. It is because the bottom surface of the tube is insulated.
Yeah, is it finished already?
Not yet, ma'am, because the problem 6.2 is skipped.
Which one is that?
I'm sorry, ma'am. Please wait for a minute, ma'am. This is for the variation 1. After we calculate each node and we transfer it to MATLAB and try to calculate it, but the result is negative, much of negative, and we have to try it berkali-kali, but the result is still negative, ma'am.
Okay. So this is for variation 1, isn't it? So what is the difference? Can you return? Is it finished already for the presentation?
Yes, ma'am.
Okay. So before that, what is the solution method that you use to solve this?
We use Gauss-Jordan, ma'am, for the calculation.
Gauss-Jordan as well. Okay. So what is the difference between the initial condition and the variation? Can you back again to the problem?
Wait, ma'am.
So I will explain. Well, this is the initial condition that has 17 nodes with delta theta 30 degree. Next. So the first variation, the delta theta changed from 30 to 15. And for the second variation, the bottom surface from 100 changed to 0. So it become adiabatic.
Okay, so you use adiabatic on the top and on the bottom, and then you have, do you have heat generation here?
No, we don't, ma'am. And the problem is in the variation 1 when we change the 30 degree to 15.
Yeah. 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 You must be careful, yeah, when doing discretization and how you do the treatment on the interface between that. So you are using as well rectangular and cylindrical coordinate.
Yes, ma'am.
Okay, so do you use the same treatment for the interface?
We use for the cylindrical the polar one, and for the rectangular the Cartesian one.
Yeah, I mean for the interface, for example, you have node 20 and 21. So how do you treat that interface?
For example, for 20, we halve it. So the cylindrical one is plus the rectangular one in PD equation.
Okay, so that might be a problem as well, yeah. I will check again how you do the discretization at that point, yeah. One thing to remember is that we are trying to solve a system here. So this is similar to the first problem from Sultan group earlier, yeah, very similar. And the problem might be almost similar, yeah, but here you have a very a negative value. And if you look at here at the problem, yeah, so you have a heat flux there, and then you have an adiabatic, yeah. So when this is possible, yeah, if you use all Newman boundary condition and you have specified the gradient there. But sometimes using all boundary condition as the Newman boundary condition, that will make the calculation almost singular. Yeah, so that it will be easier if you can combine with Dirichlet boundary condition. So if you use all Newman boundary condition, yeah, so that will be a problem with the solution sometimes. Yeah, so that will be depends on the matrix, so coefficient matrix that has been constructed from this case. Yeah, it looks like when you're reducing delta theta from 30 to 15, it means that um, is that mean that you have more nodes or not?
For the first variation, yes, ma'am.
So you will have more nodes.
Yes.
Okay. Yeah. So with increasing number of nodes, so that the system will be more difficult to be solved. And if you are using all Newman boundary conditions, so that might cause a problem as well. Yeah. So you don't have a temperature specified at any point, isn't it?
No, ma'am.
Okay. So that will be sometimes that occur. Yeah. So if we use all Newman boundary conditions, so the calculation will be floating. So there can be many solutions that will satisfy the boundary condition that you gave. Yeah. So there can be it can have many solutions. Yeah. So if you give, for example, one side to a certain temperature, so that will make the calculation stable. Yeah. So the condition number of the coefficient matrix will be better, so that you will have a more accurate solution. Yeah. So if you use all Newman, sometimes this can be occur as well. Yeah. So I think that is because the boundary condition that is applied as well. And also you have to, I will check again, yeah, how you treat the discretization, especially for the interface. Okay, any question for from the others?
May I ask a question, ma'am?
Yes.
Before you said that at least we need one side with fixed temperature.
Yes.
Is one side enough, or we need more for this case, ma'am?
Or one will be enough. Even if you want to, for example, take one point and you set the temperature for that point, it's even enough. Yeah, that's just to hold the solution so that it will have a unique solution. So if you're applying this all gradient like this one, so there can be many solutions that will satisfy this gradient. Yeah. So it will be much better if you can apply one point or one side, yeah, for several points, yeah, for the boundary sides to a certain temperature. So that will be enough.
Okay, thank you, ma'am.
Yeah. All right. So I think, yeah, we have seen several presentations. Yeah. You can close the presentations. Thank you for the fourth group.
Okay, ma'am.
Yeah, thank you for all of you who has been presenting today. Yeah, we've seen that maybe some groups encounter some problems in doing the calculations. Yeah, yeah, this is a process of learning. Overall, I'm pretty happy to see that you have yeah, that you have done the project quite well. Yeah, and this shows you that you already understand the basis for the finite difference method. Yeah, in which finite difference method is very important, particularly later if you are interested in doing finite element analysis, for example, for structure, or if you are interested in CFD, computational fluid dynamics, in which you will see a more complex problem, yeah, with a larger size of problem, yeah, very large number of equations to be solved, and also sometimes a mix of partial differential equation, for example, the elliptic problem, the parabolic problem, and also hyperbolic problem. So this will stand as a basis. So if you understand this one, I think you will have no difficulties to understand later in finite element analysis or CFD. Yeah. So yeah, that will be all for this course. I think we almost cover all of the book, yeah, almost 900 pages, although we skipped some parts, but overall we have discussed many things here. Yeah, and you have seen that nothing is difficult. Yeah, so it's based on procedure in which that will be applied in the code so that the computer can work for us. Yeah. Okay, so yeah, applause for all of you. Yeah, who have finished the project. And next week we will have a final exam. Yeah, in which for the final exam the material will be starting from the material after the midterm exam. Yeah, so that will be from curve fitting up to today. Yeah. Okay. All right. So I think you have a grab of the numerical method already, and I'm pretty happy to that. And I would like to apologize if there is any mistakes, yeah, during the course. I hope this will be useful for you, and you can gain a lot of useful information and also knowledge from this course. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Ma'am.
Waalaikumsalam warahmatullahi wabarakatuh.